Hi, my name is Yumiko Tanashell, and I completed my journal article project on cosmic voids and GAN-generated maps of large-scale structure. So GAN stands for Generative Adversarial Network. It's a machine learning model that creates new data that resembles real data. So how it works is it trains two different networks to compete against each other, which is what adversarial in the name means, to produce realistic yet artificial data, which is what generative stands for. So the two different networks are the generator, which generates fake data from random noise to resemble the real data that's provided. The discriminator is the other network, and it must identify the fake data and differentiate from the real data. So this is my review of literature. So one article mentioned that in 2004 that voids are only weakly influenced by nonlinear effects of gravity. Another one mentioned that they train GANs to map observational data to either super resolved or denoised. Another mentioned that shapes and distributions of voids provide tests of modified theories of gravity. So the gap in literature that's present is that previous research has either lacked the use of GAN technology or lacked direct comparison between GAN-generated and simulated voids, which leaves a gap in understanding their reliability and accuracy. So my research questions and hypothesis. So my research goals, the research goals of the article were to evaluate how well GANs replicate void distributions and density contrasts, to compare GAN-generated images to simulated images, and to identify specific limitations in the GAN's ability to reproduce extreme density contrasts. So the hypothesis was that GAN-generated images will closely match the overall void distribution in a CDM, which is the simulated universe, but will struggle to reproduce the smallest and most underdense voids. So this will result in a higher mean interior density contrast and systematic differences in void size and density profiles compared to simulated images in the CDM universe. So for the methodology, for the n-body simulations, they use 10 of these CDM simulations. Each simulation generates density maps of cosmic structures, and they convert these simulations into 15,000 2D images for training the GAN, because it needs real data to be input. So the second part is training the GAN, so they use the Wasserstein GAN, or the WGAN. So they train on normalized density maps from n-body simulations to learn void patterns. The generator learns to produce these realistic cosmic structures. So for the analysis, evaluating the GAN's performance was the analysis. So they compared GAN-generated images with real simulation data. They measured void distributions and density contrasts for accuracy. Also, larger scaling parameters preserve high-density structures, which another author mentioned in their article, nonlinear 3D cosmic web simulation with heavy-tailed generative adversarial networks, which is another study that involved these GANs in 2020. And they assess if GANs can replicate large-scale cosmic voids. So the statistical methods that they used were the power spectrum analysis, void size distribution analysis, and density contrast measurements. So power spectrum analysis quantifies structural similarities. Void size distribution analysis assesses the accuracy of the generated voids, and density contrast measurements determine how well GANs can replicate cosmic environments. So for the data and results, the density contrast distribution analysis computed probability distribution of matter density contrast, used all generated and simulated images. and 10,000 bootstrap samples for error estimates. So the key findings of this data were that the WGAN underproduces higher density pixels, and it impacts central and mean interior density contrast of voids. So this is the graph that came out of this data from the density contrast distribution analysis. And so for the power spectra calculation, a computed mean power spectra from simulated and generated images, they use NumPy for Fourier transform, which is Fourier transform of the density contrast field in the equation for the power spectra calculation. And then they used 10,000 bootstrap samples for error estimates. So the key findings were that there was a good agreement on scales, and there was a possible impact on large-scale void statistics. So for the discussion and conclusion, the key findings were that the WGAN-generated images are similar to n-body simulations, but there are differences in void properties. Generated images have fewer small and empty voids. Void counts are close, but generated images have fewer and fewer small and empty voids. So the WGAN has trouble capturing extreme high and low density contrasts. So the sources of error for this study was that neural networks capture general trends but can miss extreme values, which can skew the results. So for the hypothesis evaluation, WGAN generates structure maps well, but it needs improvement in void statistics. So for applying this to future areas of research and to the real world, GANs can be an alternative to costly n-body simulations because they're much cheaper to run, and they're useful for studying voids in cosmology. For future research, they can test with advanced GAN models for better void accuracy. They can compare them to other generative models, like this other author did in 2020 with super resolution emulator of cosmological simulations using deep physical models. So these are my references.